Okay, so let's do a concrete quantitative example of how a probability changes when you get new information. Okay, so think of a school, for example, RPI, and let's say that number of students is equal to 5,000, and CS, being the biggest major, has 1,000 of these students. So number for CS is equal to 1,000. Okay, and math is about 1/10 of CS, so the number of math equals 100. Okay. And some students are math CS duals. So, math CS duals, well, that's equal to, CS intersection math. Let's say that's 80. Okay. And we can represent this on a Venn diagram if we wanted to. So the picture would look something like this. Okay, so this is all students. Okay, and a large fraction of these students are CS, so a large fraction are CS, so that's CS. Okay, and 1/10 of that are math, so some amount of these are math, but a large fraction of the math intersects with CS because 80 of these math students are also CS majors. So very similar to the profile in RPI, for example. So a large fraction of the students who are in math are also intersecting with CS. So math is 100 and this intersection region is 80. Okay, now we're going to imagine an experiment. Pick a student randomly. Pick random student. Okay, so what's the sample space? So sample space omega is, all the possible students can be the outcome. Is all 5,000 students. Okay, and each outcome corresponds to a single student, and each student is equally likely. So, we're in a uniform sample space, and we can ask, what's the probability that you picked a CS student? Okay, so that's the question. How likely is it that you picked a CS student? The event that corresponds to that question is the set of CS students. Remember, an event is a subset of all the possible outcomes. So the probability of CS. Okay, and now in a uniform sample space, this is the size of the event divided by the size of the sample space, because we're in a uniform sample space. So things get much more convenient and easier when we're in uniform sample spaces. You don't need to go through all the details of the outcome tree and so on and so forth. We can immediately look at the outcomes and assign them an equal probability. Okay, and so this is 1,000 divided by 5,000, which is 0.2. So the chances are 20% that if you pick a random student in this scenario, in this experiment, they will be a CS student. No surprise there. Okay, we could have figured that out. One in 5. Okay, now you picked a random student, and I'm going to give you some new information. They're a math student. Okay, the student is in math. Okay, so this is new information. And let's see what it does. What does this new information do? Effectively, it shrinks the set of possible outcomes. Okay. Before, when I just said you picked a random student and you had no additional information, all 5,000 students were possible. They were possible outcomes, and so that was your sample space. But now that I tell you the student is in math, that eliminates, a lot of those possible outcomes and says that your possible outcomes are now in this set, which is math. Okay. So all of a sudden, your sample space, the set of possible outcomes, your sample space became just the set of math students. That's effectively what this piece of new information does. Okay. Now we can ask, what's the probability of what are the chances that this student who was random, but now we have the new information that they're in math, what are the chances they're a CS major? So we can ask, what are the chances that the student with this additional information is in CS? And the way we indicate that we have this additional indication, we say probability of CS given math. Okay, and so this is, the size of the event in this new sample space that corresponds to CS. But the size of the event in this new sample space that corresponds to CS, the event itself, the set of outcomes that correspond to CS in this new sample space, is exactly the students in this region. Okay, because those are the CS students in this new sample space of possible outcomes. Okay, so the probability of CS given math is the size of this event. But what is this event? That's CS intersection math. Because it's a uniform sample space, okay, because it's still a random student who happens to be math. So it's the size of, the event in this new sample space divided by the size of the sample space, which became math, okay, which is equal to the CS intersection math. The size of that is the number of CS math duals, that's 80, divided by the size of math, 100, which is equal to 0.8. Interesting. Okay, so you see how the arrival of new information changed the probability. So before, when I just picked a random student, the chances are 20% that they're a CS major. Now, if I pick a random student and find out they're in math, the chances are 80% that they're a CS major. Okay. Huge change in the probability. Now, practice. Compute the probability that, a random student is a math major if you are told the additional information that they're in CS. Okay. And compute the probability that a random student is a CS major if you're told the additional information that they're in CS or math. Okay. So, this is practice for you to see if you can apply this reasoning to these two problems. Okay, and we'll move on. Okay, because the uniform sample space where you pick a student randomly is just a special case of an experiment. So let's move on to the more general case of an experiment and see how new information in a more general setting updates a probability. Okay, so this is now the beginning of what we're going to call the definition of conditional probability. So conditional probability. Okay, so the way we write this is you have two events A and B. Okay, so you have a sample space omega. Space. And you have two events A, that's an event, and B, that's an event. Okay, and we write the probability of the event A occurring, okay, given that B has occurred. Okay, so the probability of event A occurring given that B has occurred, and this is read, the probability, the conditional probability, So conditional being says that, I'm conditioning on the information that the event B has occurred. So conditional probability of A given B. Okay, and this vertical bar is what indicates the given B. Okay, so probability of A given B. Okay, and let's try to work this out. Okay, now, you're doing an experiment, okay, and there's the whole sample space of possible outcomes. So when you're doing this experiment, I'll just heuristically say that, so this is one experiment, this is another. So if you repeated this experiment many times, okay, you get outcome. All these outcomes are in the sample space. And some of these outcomes are in the event B. So what does it mean, in the event B? Doesn't an event just happen? So now you have to go back and remember that an event is a subset of the outcomes. So when an outcome occurs, okay, we can ask, is it in the subset B? So in some of these outcomes, the event B occurred. Let's call it N sub B. In some of those outcomes, the event B occurred. Okay, so if I tell you now that the event B has occurred, then these other outcomes could not have happened. So this becomes your effective sort of sample space of outcomes that are, possible. For you've eliminated these outcomes. Okay, if I tell you that B occurs. Okay, now in some of these outcomes, A occurs. Okay, in some of these outcomes, A occurs. Okay, and then in some of these outcomes, which are box, okay, A and B occur. So A and B. Okay, now if I tell you that B has occurred, that eliminates all these outcomes, and associated with those outcomes that are the ones that A occurred without B occurring. Okay, so if I ask you now, given that these outcomes did not occur, okay, so it means that when you repeat this experiment many times and make use of the information that that the outcomes in B did not occur, you can eliminate these outcomes. Okay, and so the outcomes that become of interest to you are exactly these outcomes. Okay, and so if you repeat this outcome in which you are guaranteed that B occurs, okay, you'll get n sub B outcomes. And by the frequency interpretation of probability, the probability of A, given that B has occurred, okay, is the fraction of those outcomes in this repeated experiment where A occurred, okay, which is n sub A intersection B divided by B, divided by n sub B. So think of it this way: you've run an experiment, okay, and you are now told that B occurred. So you know that the outcome is in B. So it's not one of these. It's this guy, let's say. And then you ran the experiment again, and B occurred, and B occurred, and B occurred. And now you're interested in what's the probability that A occurs, given that B occurs. Okay. So by the frequency interpretation of probability, the probability that A occurs, given that B occurs, is exactly the number of times A and B occurred, divided by the number of times B occurred. So this is, let me write this as, this should approximate that. So whatever this is, it should approximate that. Okay, but now let's rewrite both of these quantities by dividing and multiplying by n. Okay, the total number of times the experiment was done, and then you threw away some of those. So this is equal to n sub A intersection B divided by n. The complication here is the n sub B in the denominator. So n sub A intersection B divided by n times n divided by n sub B. Okay, this is just an equality. Okay? I can write this expression as the number of times A and B occurred divided by n times the number of times B occurred in the denominator with n on the numerator. So this here is the frequency interpretation of the probability. So this is still a probability of A. It's just in this restricted situation where B occurs. So this is the frequency interpretation of probability. Okay? And this is just an equality. You can't argue with that. But now I'm going to use the frequency interpretation of probability again. And we know that, if you run the experiment n times, so this is all the n times you ran the experiment, n sub A intersection B divided by n, this is exactly the probability that A intersection B occurs. Remember, A and B are events, so I can take the intersection to get another set, which is an event. Okay? And this is exactly, 1 over the probability that B occurs. 1 over the probability that B occurs. Why? Because the probability that B occurs is the number of times it occurs, approximately, in the frequency interpretation of probability. It's approximately the number of times that B occurs divided by n. So this, again, is the frequency interpretation of probability. In this case, it's the frequency interpretation of the probability that the event A intersection B occurs, and this is the frequency interpretation of the probability that B occurs. And here, we gave a frequency interpretation of what it means to consider the probability of A given B. You're considering the how often the outcome is in both A and B, as a fraction of this restricted universe, this restricted sample space of only outcomes in B. Okay? And so, what this means is that if we define this conditional probability as this quantity, then it will indeed be the case that when you run this experiment many times and you look at the number of times A and B occurred divided by the number of times B occurred, you will get, this quantity, okay, which by definition is now the conditional probability. Okay? So what we have derived / defined, so definition, the conditional probability P of A given B is equal to the probability of A and B divided by the probability of B. Okay. Definition. Now, you might look at this and say, this only makes sense if the probability of B is not equal to 0. And that is the case. Okay, so this assumes that when the probability of B is not equal to 0. So this is a definition of the conditional probability. Okay, now we're going to do several examples. Okay, so let me erase, come back and do some examples. So that's the definition. What's the interpretation? The interpretation is, initially you might have had the probability of A. So you had the probability of A. And now when you tell me the event B has occurred, I update the probability of A to the probability of A given B, which is given by this definition, which corresponds to, observing the experiment many times and looking at how many times both A and B occurred, divided by the number of times that B occurred. Okay. Now I want to emphasize, even though it's wrapped up in this fancy language, it is still just a probability. It's just that it's still a probability for outcomes in A. It's just that we have narrowed down the scope to now knowing that B has also occurred. So it's still the probability that A occurs. It's just that it's an updated probability for A. It's an updated probability for A given that B occurs. Okay? Examples.